In this video, we'll continue the derivation of a simplified model for a resonant wireless power transfer system. So basically, at the end of the day, as we saw in the previous video, essentially we have the transmitter, and we mentioned that the wireless power transfer coil essentially or transformer can be modeled as an inductor in series with an ideal transformer. And so, if we assume the ideal transformer essentially is 1-to-1 ratio, we can just move the full bridge rectifier and the DC load to the primary side. And of course, we use a capacitor to tune out the series inductance of the coil. Now, in this video, we'll find that all of this, can be replaced simply by a single resistor Ri that's equal to 8 over pi square times the load resistor, the DC load resistor R. So essentially, the equivalent resistance of all of this, or the full bridge as well as the DC load, at the end of the day, the transmitter or the AC side sees the load as just simply 81%. This number 8 over pi is essentially 0.81 81% of the DC load resistance R. So how did we arrive at this conclusion? Well, to find the equivalent input resistance of the bridge rectifier as seen by the AC side or the transmitter, essentially the resonant converter or the resonant inverter, well, we need to find the voltage. We need to find the voltage across the bridge rectifier, and we already know the current that's flowing through the series resonance circuit, and we know that it's sinusoidal. From a previous video, we find that it's a sinusoidal current with an amplitude I max or Im times sine omega t minus psi, and so essentially we have some phase lag minus psi. So once we find the voltage across the full bridge rectifier, we extract the fundamental component, or essentially the equivalent input impedance Ri will be basically the ratio between the voltage across the bridge rectifier, this voltage here, divided by the sinusoidal current I. Okay, so let's see the operation of the full bridge rectifier, and let's try to find a waveform for the voltage V. First of all, we mentioned that typically the quality factor of a series resonant inverter is by design larger than 2.5, and the reason is in order so that this series resonant circuit essentially acts as a bandpass filter with low bandwidth or small bandwidth, so that it extracts the fundamental and rejects with enough rejection the third order harmonic and the higher order harmonics. Okay, and enable a pure sine or almost a pure sine in the series resonant inverter. Okay, so by design, the loaded quality of a series resonant inverter should be larger than 2.5. And under this condition, we'll find that the series resonance circuit essentially behaves as a current source. And this means if we sketch this part again, we have this is D0, D1, so under this condition, as I just mentioned, we'll find that the series resonance circuit essentially behaves as an ideal current source. So basically, we can just replace all of this part simply by a current source. and the value of the current source is I, where I is given by this sinusoidal expression. Okay. And the reason for that, we will find if you simulate the circuit, and you will find that by changing the voltage here, essentially this voltage is not going to affect the current that's going through the series resonant circuit. So basically it behaves almost as an ideal current source. So as a first order approximation, we replace all of the transmitter or the half bridge as well as the series resonant circuit with just a current source I. Now, if we look at this current source and how the full bridge is going to operate, well, this current is sinusoidal. So we have a sine here, periodic sine of course. So during the positive half cycle, the current is positive. So the current essentially will flow here. It will come here. Well, it can't go through D0. So it will go, it's going to go through D1 and reaches the load. And then via the ground is going to go here. And in this case, we'll find that it's going to go through the essentially this diode and continue the flow in the circuit. And so during the positive half cycle, essentially we'll find D1 and D3 are on, as shown here. So this is D1 and D3. So the odd numbered switches, or sorry, the odd numbered diodes are on during the positive half cycle. Now, during the negative half cycle, so the current basically is flowing in this direction. So it will flow via D2 to the load. Again, the current here is basically positive from left to right in both cycles. In the positive cycle, it's from left to right. And also in the negative cycle, since it comes via D2, it's from left to right. So essentially the current that's being delivered as output current from the rectifier. So the current here is basically the absolute value of the sinusoidal current I. And basically, if we look at the output current of the rectifier, it will take the negative half cycle and flip it upside down, and essentially it will become positive. So this is the current, the output current from the rectifier is going to be the absolute value of the series resonant circuit current I, or this current source I. So to continue, the current will flow in here, going into the ground. And since the current is basically in the negative half cycle is flowing counterclockwise, so the only way for it to flow is via D0, not via D1, right? Or the return current will come via D0. So in this case, D3 is off, while D2 and D0 are on. So the even numbered diodes, D0 and D2, are going to be on, while the odd numbered are off. So in the positive half cycle, D1 and D2 are on, D1 and D3 are on, the odd numbered are on, while in the negative half cycle, we have D0 and D2 are on, the even number. And now we know that the current, the output current from the full bridge rectifier is going to be in the positive half cycle, is going to pass the positive half cycle of the source current I, while flipping upside down the negative half cycle. And since the amplitude of this current is what? Im. So basically, the peak value of the rectified voltage is Im. This is the output current from the full bridge rectifier, the current at this node. Now the average value of a full wave rectified signal, you can do the integration and you'll find that average value is equal to 2 over pi times the current Im. And so that's really good, because now, since this current, as I mentioned, just to resketch here, is going to be a full wave rectified signal, and its average value is 2 over pi Im. Now, this current, as you can see, will have high order harmonics in addition to the DC component that's given by 2 over pi Im. So if we sketch this in the frequency domain, it will have, so this is the output current from the rectifier. If we sketch it in the frequency domain, we'll find that it will have a DC component at 2 over pi Im, as well as higher order harmonics. Okay. Now, to reject the high order harmonics, we connect in parallel with the DC load a very large capacitor C. And since this circuit, RC circuit, is linear, we can apply KCL at this node for each frequency component at a time. So we can apply it at the DC component first, and then we can apply it at the first or fundamental component, the second harmonic, the third harmonic, and so on. So at the fundamental component, we know that the equivalent reactance of the capacitor is going to be 1 over J omega C, and since the frequency is 0 at DC, so it is going to essentially approach infinity. And essentially the capacitor will be an open circuit. So all of this DC current is going to flow into the DC load, or the DC resistance. So the DC component of the rectifier current, this 2 over pi Im, will flow into the DC load. And so the value of the DC voltage now is simply what? Is going to be the current, the DC current, 2 over pi Im, times the load resistance R. However, this is under the assumption that this capacitor C is very large in value. Why? Because when this capacitor is very large in value, if we do KCL at the fundamental frequency, for example, we'll find that the equivalent reactance of the capacitor will be over 1 over J omega C, say omega 1 at the fundamental component. And if we assume that the absolute value of the reactance, essentially 1 over omega C, is much smaller than the load resistance R, then all of the fundamental component is going to flow in the capacitor. Essentially, the capacitor is going to shunt the first order harmonic. And the same thing, of course, it will shunt the second order harmonic, third order harmonic, and so on. And none of these harmonics will be or will reach the DC load R. Okay, so obviously this capacitor is used for filtering or extracting, removing, shunting all of the harmonics away from the DC load. And so all the DC load will only see the DC component of the rectified current, or the full bridge rectifier output current, which is equal to 2 over pi Im. And so the DC voltage will be 2 over pi Im times the DC load resistance R. Now, what we are interested in is to find the equivalent input resistance of that's seen via the full bridge rectifier, or how the AC side sees the full bridge rectifier if we model it as an equivalent resistance Ri. And to do that, we need to find the voltage across the voltage here. We already know the current. Now we need to find the voltage, and the ratio between them is going to be the equivalent resistance of seen into the full bridge rectifier. And well, as I mentioned, this is the current, the output current of the full bridge rectifier. This is the resonant tank current I. And so during the positive half cycle, as I mentioned, we'll find that the odd numbered diodes are on. And so essentially the voltage here is VDC, the DC voltage. And all of VDC will appear across the current source with positive polarity at the top. Then, in the negative half cycle of the current, we said that the odd numbered switches, or sorry, the even numbered switches, D0 and D2, will be on. And so, as you can see here, the positive terminal of the DC load, or the voltage VDC, is essentially connected to the bottom terminal of the current source. So essentially, the VDC will appear upside down with positive polarity at the bottom across the current source. So in the positive half cycle, VDC has positive polarity, or the voltage across the current source is equal to VDC in positive, while in the negative half cycle, the voltage is equal to, across the current source, I is equal to minus VDC. So it's a square voltage. And we know that this square voltage with VDC and minus VDC, within it has a fundamental component, sinusoidal fundamental component, as shown here with this dashed line. And this fundamental component, the amplitude of it is equal to 4 over pi times VDC. Okay. And then, of course, this square voltage will also have a higher order harmonics. So if we sketch versus frequency, first of all, since this is a bipolar voltage between VDC and minus VDC, we'll find that the average value of it, or the DC component, will be 0, while the fundamental component, as I just mentioned, is going to be 4 over pi times VDC. Then we have a third order harmonic, so this is at F, this is at 3F, and 5F, and so on. Now, out of all these harmonics, since the current I is a pure sine, and this pure sine is at F, or at 6.78 megahertz in our resonant wireless power transfer system, we will find that the only harmonic that will carry power to the DC load will be the fundamental component that's at the same frequency F. Because the average value, because eventually the power that's real power that's transferred from the AC side to the DC side will be what? Will be the average value, which is the integration of this current I multiplied by the voltage here. And this voltage, we said it consists of a fundamental component, V1, third order component, fifth component, and so on, higher order harmonics. And if we perform this integration, we can expand the term inside as I times V1 plus I times V3 plus I times V5, and so on. And then we have 1 over 2 pi, integration from 0 to 2 pi, I times V1 d omega t, plus 1 over 2 pi I times V3, and so on, right? We'll find that the integration of two frequency components, this is at the fundamental while this is at the third, essentially they are orthonormal, so essentially their average value is going to be 0. And the only component, the same thing for the fifth, seventh, and so on. The only component that will survive the integration, the average integration, is just the fundamental component. And that's why I say the only component that of the voltage, since it's square, it has fundamental higher order harmonic, the only component that will carry power to the load, average power to the load, is just the fundamental component. So again, we have I times V1 plus V3 plus V5, and so on. The only component that will carry real power to the DC load is just the fundamental component V1 of the voltage across the current source, which, as we found, is a square voltage. Now, what we were interested in finding is basically the equivalent input resistance of the bridge rectifier, full bridge rectifier. And so Ri will be equal to basically the amplitude of the fundamental component of the square voltage, the voltage across the current source, divided by the amplitude of this current I, which is Im. As I mentioned, the higher order harmonics, they don't carry any power, okay? So they will not cause any real resistance, essentially, okay? And so V1, we said, is equal to 4 over pi, the amplitude of the fundamental component is going to be 4 over pi times the DC voltage VDC divided by Im. And the voltage VDC, we mentioned that the DC component of the rectified current is equal to 2 over pi times Im. And so the voltage here will be 2 over pi Im times the load resistor R. So we have 4 over pi, and then we have 2 over pi Im times the load resistor R divided by Im. Im will cancel Im, and then we have 8 in the numerator over pi square times the load resistor, the DC load resistor R. And that's why at the very beginning I mentioned that all of this, all of the DC sides, the full bridge as well as the DC load at the end of the day can be modeled by an equivalent resistance that's equal to 81%, 8 over pi square times the DC load resistance R. Or in other words, the AC side sees the DC load as 81%, or only sees 81% of its of the DC load resistance value. And so going back to the schematic, the original schematic, all of this at the end of the day can be replaced by a single resistor that's equal to 8 over pi square times R, where R is the DC